Right. Here we go. Happy Friday. Happy Friday. All right. So, a couple things. There are weird words, right? You did your first Mad Minute. It's a little different. They're kind of long, bigger words. So sometimes, like Esker was a weird word, but it's shorter. Bless you. We have a lot of like the lithosphere, mesosphere, asthenosphere. Sphere means ball, or like a sphere is like a solid circle, right? So if you think of sphere, you're talking kind of like one of those layers. And then like you have another layer on top of it and another layer on top of it. So kind of like concentric circles, like where you just keep adding on, adding on, adding on. Those are all considered spheres, okay? And then today we're going to talk about what those prefixes of litho, astheno, and meso mean. And so that might help you keep the different words a little bit straight. So we'll work on the vocab. Obviously, we're just at the very beginning. So we looked at our crust. What were the two types of crust? Give me one. Continental. And what is on continental crust? Yeah, like land. All right, what's our other one, Sarah? Good. And what is above our oceanic crust? Ocean. Good. So you have that pretty shocking information there. We know that the oceanic crust is a little bit thinner. It's more dense because it has all the pressure of the oceans over it. And then the continental crust is typically a lot thicker. So going from here halfway to Galleon would be about 4 miles, and that's about as thick as the oceanic crust typically is. It's made of that volcanic material, and we'll get to why that is later. And then our continental crust is about, on average, 25 miles thick, and that'd be like driving from school to Marion. Okay, so that's kind of where we are. We're starting into our second major group, because we have three major types of layers. We have our crust, we have our mantle, and our core. So crust has 2 parts, and now our mantle is going to have 3 parts. Okay. And the mantle is by far the largest. It's about that 80% of our total volume of our Earth, and it is split into 3 parts. So the crust is split into 2, the mantle is split into 3, and then our core is also going to be split into 2. Okay. So the first part is the lithosphere, and this part is kind of special, a little bit fancy, because it's actually including 2 things. It's going to count the crust layer, that mohovaric discontinuity, or like that moho boundary that I said is kind of, it's not composed of crust and it's not composed of mantle. It's a little bit different. So to me, it's kind of like the sauce on pizza. You have the crust, you have the sauce, and then you have your toppings and cheese. Well, you have your crust, you have your moho discontinuity is kind of like the sauce, and then this would be kind of like your getting to the crust, okay, of the pizza, not the layers of the earth. So the lithosphere is going to comprise both of those. It's the very upper mantle and whatever crust is involved, whether it's continental like on this side, or if you're looking at this side, it'd be oceanic crust and your upper mantle. So it's counting both of those things, and that's the only layer that's like that, okay? So we know it's the upper mantle, but when it's included with the crust, we call it the lithosphere. Litho means rigid, kind of rock-like. Well, that makes sense because that's including the crust, the continental or the oceanic. So it's hard, it's rocks that are making it up. The upper mantle is also very stiff and rigid. Okay. So litho means rock-like. Right? And then we're going to move into the asthenosphere. Right? Oops. And astheno means weak. The reason it means weak is because it is actually the softer. It's kind of not quite liquid, but not quite solid. When you think of lava coming from a volcano, that is kind of what the asthenosphere is. It's real thick, real flowy, and it is going to be right here. Okay? The special thing, I'm gonna back up, sorry, get too clicky. The special thing about the asthenosphere that you need to know is this is where the convection currents take place. And we're gonna talk about what convection currents are. Should sound somewhat familiar from last year, and we'll talk about, see if anybody remembers that from last year in a minute. So asthenosphere is kind of like this middle mantle layer. Okay, so we have the upper, which is included in the lithosphere. We have the asthenosphere, and the important part here is this is where the convection currents happen. Okay, and then we have our mesosphere, and this is the very lowest part of the mantle, the one that is closest to the core. Right, so it's the very bottom of the mantle, but meso all actually means middle. And so it's like, whoa, that's confusing, because you think, okay, well, if you have three layers of, or three parts of the mantle, you would think meso would be the one in the middle. The reason that it is called the mesosphere is because it's kind of the middle of our earth. If you would go from the crust, dig to the core, the mesosphere is about halfway down. So that's why it gets that name. But if you just kind of remember, you go lithosphere, asthenosphere, mesosphere. Starting with L, A, and then M. Right? L for lithosphere, A for asthenosphere, M for mesosphere. And really there's nothing too special about the mesosphere, except that it is the closest to the core. So nothing too spectacular happens there. This is sometimes considered the lower mantle. I'm not going to need you to be able to identify that, but you'll probably see that on some diagrams and pictures and things. So this would be considered the lower mantle, and you see that right here. And then these two are typically considered to be the upper mantle. And then obviously the lithosphere is not only mantle, but it's including that crust as well. Thank you. Have a good day. Okay. So again, we're gonna do a lot of practice with this, and you're probably like, oh, I'm never gonna keep all this straight. It's really not too terrible. You're gonna need to know, obviously, the two kinds of crust, the three types of mantle, and then the two types of core that we're gonna get to. Okay. All right, convection currents. Who remembers what convection currents are? Can you show me, maybe even with your, with your hands, maybe what they do, Abby?
Like in a circle.
Yeah, it's kind of going.
With like the heat and it like cools down and stuff.
Okay, so you're talking different temperatures, right? So things are kind of going around. Good, so where did you guys talk about this? Or like what unit or what was it related to, Jackson?
I think it was in like the ocean currents.
Okay.
Yeah.
Good, ocean currents. Did you maybe talk about like wind, with wind as well? Kind of like when you talked about trade winds and, good. Very good. I always let Mrs. Heil know if, how well you guys kind of remember that. So, awesome. So we have the same exact process, but now it's not in an ocean and we're not talking in a gas, like in our wind or air. We're talking about in the asthenosphere area. Excuse me. So, these are the currents that transfer heat from the Earth's interior. Earth's interior. So the core, which is right here, is hot, very hot, right? So if it's hot, it's gonna be heating up the mantle, okay? And so we're gonna look at this process, and you can see all these different kind of circular patterns, right? All throughout, they all go all the way around the core, okay? Little cells, convection cells or pockets, where these currents take place. And this is super important because this is the driving force of plate tectonics, which is going to be our next unit. Without these convection currents or without the heat that is in our core causing these convection currents, we would not get a lot of the features and things that we have on our surface that we experience, like the volcanoes, earthquakes, which obviously aren't like something we want, but it's something that is existing because of it. We wouldn't get new crust being made. So there's a lot of things that have been affected because of this heat source causing the convection currents, and then it causes other things that we see here on our surface. Bless you. And so again, the important thing, so you can kind of see this is the crust, this is the upper mantle, and this would be considered our lithosphere. Directly below the lithosphere is our asthenosphere, where we're talking, the convection currents are found, okay? And so that is the key. That's what you need to know about the asthenosphere. That's where you find those convection currents. So here's how they work. And you are gonna need to kind of have the general basics of this, all right? So molten material, molten meaning hot and melted rock, right, is in the lowest part of the asthenosphere, closest to the core, so it becomes warmer. Think of standing by a bonfire. The closer you are to the bonfire, the warmer it is, right? So the closer the layer is to the core, which is like our bonfire inside our earth, that's gonna be what's warmer, okay? So that material gets warm. Well, we know that when things heat up, they become less dense. Dense means how tightly packed something is. So if it becomes less tightly packed, it's going to rise, okay? Less dense will rise. Slowly works its way to the top of the asthenosphere. So this is a very progressive type of process. You have the heat, it warms the material. The material becomes less dense because it's hot, and then it rises. Well, what happens when you move away from that bonfire? When you step back like 10 or 15 steps, what happens with how you feel? You still feel so much heat? No, you cool off. Well, if the less dense material is rising away from the heat source, just like you stepping back from a bonfire, it starts to cool off, right? And that's exactly what happens with the magma, or that molten material of the asthenosphere. As it gets to the top, it gets cooled off too. Well, cold things, they're gonna condense and get more dense, get more tightly packed, okay? And so when that happens, if it gets more tightly packed, is it gonna continue to rise, or is it gonna sink? It's gonna sink. So this process, you just need to think about it common sense and logically, right? Now as it's sinking back, what's it getting close to again? The heat source. So what's gonna happen to it? It's gonna get warmer. Uh-oh, when it gets warmer, less dense is gonna rise. Gets away from the heat, cools down, becomes more dense, and sinks again. And so you get this continual cyclical kind of pattern. Unless the heat source goes away, this process is gonna continue. The thing that's driving this is the heat. Okay, so if the heat goes away, then we would have a stop in these currents. But as long as we have that heat source, it's gonna continue. Okay? So as it becomes cooler, it becomes more dense again, and it begins to slowly sink back down. So I have a couple ways to help you think about this logically, like related to your real life. When you're hot, do you want to be like all curled up, or when you're hot, you want to spread out? Spread out, right? That's what all matter wants to do as well. And that magma, that molten material, that melted rock of the asthenosphere is that way. So when it gets hot, it spreads out. When it spreads out, then it can rise, right? When it's up there, we know it's away from the heat, so it gets cold. What do you do when you get cold? Ooh, right? I see some of you like bundling in. That's what I do, right? When I get cold, I'm not like, oh, wow. Heck no, like you want to like, right? Get all bunched up, try to conserve your body heat. Well, the magma does the same thing. Those molecules come together. And as they come together, they get packed in more tightly and they get more dense. Well, we know more dense things are going to sink. And when they do, now they're back to the heat source again. Then they want to spread out. Then they get more dense or less dense and rise. Get away from the heat, get cold, come together, and drop. Try to start using it in between classes so you're not missing. Today will be the last day I'll let you go, but yes, quickly. Try to get back as quick as you can. So think of it like that. What do you do when you get hot? What do you do when you get cold? The magma in the asthenosphere is going to do the same as what you would do. The other thing, does anybody have an upstairs in their house? Okay, so in the summer, where is the hottest part typically of your house? Upstairs. No matter how good your heating and cooling and air conditioning systems, and your circulation of that air is, it's always gonna be hotter upstairs, right? Hot air rises, right? And you probably talked about that. That's what kind of helps generate some of our wind patterns, across our earth, right? So same idea, that hot air is gonna rise because it's less dense. We have ceiling fans, right? Ceiling fans can help try to push that warm air down. So even in the winter, a lot of people will run their ceiling fan because the heat that they're pumping into the room, well, we're not up there at the ceiling, right? We're not getting the benefit of that heat if it's up there. So we have the ceiling fan on to help push that warm air kind of gently back down to where we can use it, and that way maybe we can be a little bit more efficient with how much heat we need. So again, you can kind of think of it as common sense, and things that you have experience with. The magma is going to work the same way. Hotter, less dense, colder, more dense. Less dense always rises, more dense always sinks. Okay, so keeping those things in mind, really just applying it to these convection currents isn't really anything new. It's all just kind of common sense and logic. All right. And so the cycle just continues over and over and over as long as we have that heat source. All right, and so here's our heat. And I like the colors because obviously the red and the orange kind of mean hot. So they're getting warmed up. Now they're getting cooler. As they get cooler, they're gonna sink and then they get heated back up again. This can also happen. Here's our heat source. This happens in water. We're gonna talk about plate tectonics next unit. And so actually the plates in the lithosphere kind of rest on top of that asthenosphere. And so they actually get moved like these little blocks of wood. And you can see the plates here. And again, we'll get into that more. But because those convection currents are moving, anything on top of it is gonna kind of get pulled. Think of like having a raft in a pool. Like if you have like a floaty or an inflatable in a pool, and you like move the water underneath it, doesn't it cause the raft on top of the water to move? You're not pushing the raft, you're just moving the water underneath it, and you can get the raft to move. And so that process is kind of what's happening with our plates that are resting on that gooey, hot mantle magma material. All right. We're going to show, we have a couple videos that are going to show this, but I want to finish a couple slides first. All right, so the core. So we have our crust, which has 2 parts, we have our mantle, which has 3 parts, and now we have our core, which has 2 more parts, right? The core, kind of like an apple core, it's in the center, right? It's in the very farthest from the outside. It's the innermost layers of the earth, and it has 2 regions. We call one the inner core and one the outer core. They actually have very, very different physical properties. They're both considered core, but they are very unique. This diagram is incorrect. A lot of these are going to show the core way too big. Which one of our layers did we say takes up the majority? Brooklyn? The mantle. It's not very thick here. Really, the mantle should probably be taking up about that much space. So a lot of times, and I don't know why this is such a commonly incorrect theme, but they make the core way too big. All right, so I just want to kind of point that out. Crust looks good, it's really thin, but our mantle, too much. Okay, so we're gonna start with the outer core. That's what we get to first. And again, the outer core, they're making these cores way too big in this one as well. So the outer core is the one that's next to the mesosphere. So we go crust, which includes the top portion of the mantle to include our lithosphere, then we have our asthenosphere, then we have our mesosphere, which has nothing really fancy or special except that it's the closest to the core. Now we get to the outer core. It is considered liquid. It's liquid because it's so hot. This is our only true liquid layer. And it's about 1,400 miles thick. Okay. And so this is the the area of our Earth that is responsible for us being magnetic, for our Earth having a magnetic field around it. Right, so that's what's important. It's liquid and it is the generating force of our magnetic field. Right, so those two things are very important, and you will need to recognize that those go with the outer core. The inner core, or first of all, why do you think the outer core would be liquid? Why would it be liquid? Okay, so she said it's like the hottest. It is. It's very hot. So when something gets really hot, it melts. So basically, it is melted iron, nickel, alloy, some rock, but a lot of that metal material, it's melted. It's so hot, it is melted. Okay? So, the inner core is the only one that's an actual true sphere or circle, right? Everything else just kind of like coats that inner core. Okay. It has a radius of about 750 miles, which would be like going from like here to Tulsa, Oklahoma. It is the very absolute center of the earth, but it is the absolute warmest, hottest part of our entire planet, but it's a solid.
Pressure.
Absolutely. It has all the other layers pushing down on it, all right? Because from every direction, it is getting this immense pressure and force of all the mass up above it, it turns it into a solid. So if you adjust the pressure, it changes something's boiling or melting point. And you'll learn more about that a little next year and when you get to chemistry. So if you fiddle with the pressure of something, you can change the boiling and melting point. Okay, so that's what's actually happened. Everything, all the other layers are pressing down. What are we out of here? So I just looked at the clock and I'm like, wait a minute, what? 8:30. Okay, whew. Sorry, I just had a minor freak out for a second. I forgot we were on the 1 hour early release. Whew. Okay, so 8:30, good deal. So it has every other layer pressing down on it. And so the further you go, the more dense the layers become. That's in general. So crust is the least dense. As you go through the lithosphere, the asthenosphere, the mesosphere, the outer core, the inner core, it just gets more and more and more and more dense. Making the core, the inner core, the most dense center. So there's actually 3 things that increase as you go down, and we have a song that you will like that will help you remember this. As you go down, the pressure, the temperature, and the density all increase. So that's really nice. So if you remember the order, I always like to start at the crust, work my way down, temperature, pressure, density are all increasing, crust, mantle to core, as you work your way from the top going to the center. Okay, so we will stop the notes there.